Welcome to the Explainer. Today, we're stepping into the shoes of cosmic detectives to tackle one of the absolute greatest cold cases in the history of science. We're going to explore some thrilling new research that might just give us a way to finally see the unseeable. So get ready, because this cosmic mystery is absolutely fascinating.
It's kind of the ultimate paradox, right? I mean, how do you catch a particle that is entirely invisible? As astrophysics fans, you already know our field constantly forces us to hunt for things we just can't see directly through a telescope lens. We have to look for shadows, whispers, and footprints left behind by things that absolutely refuse to step into the light.
Okay, let's dive right into this because the stakes of this cold case are just staggering. A massive 85% of the universe's total mass is completely missing from our sight. 85%. All the stars, the planets, the gas clouds, the whole shebang that we can actually physically see or touch, that only makes up a meager 15%. The rest is what we call dark matter.
All right, Section 1, the missing mass mystery.
So we really only know this giant chunk of missing mass is out there because, well, we can see its gravitational pull on the galaxies we can see. For decades, this elusive substance has just stubbornly refused to interact with any of our instruments. It doesn't reflect light, it doesn't emit light, and it doesn't block light. It basically acts as the ultimate cosmic ghost, betraying its presence exclusively by the way its gravity pulls on observable matter, dictating the motions and arrangements of entire galaxies.
Which leads us to Section 2, decaying into gravitons. We finally got a new suspect in this mystery, and it's thanks to some really fresh, fascinating research published recently in Physical Review D by a team led by David Dunsky over at NYU. They've put forward the super tantalizing hypothesis: what if our suspect is actually a bit unstable? They're suggesting that dark matter might not be perfectly permanent. Instead, it could be slightly unstable, meaning its constituent particles are gradually decaying, just breaking down over these vast cosmic timescales into an entirely new particle.
And what exactly is it decaying into? Well, enter the graviton. A graviton is this hypothetical particle that physicists believe actually carries the force of gravity itself. Now, this is where it gets a bit tricky, because much like dark matter, the graviton has literally never been directly detected by anyone. So yeah, we are essentially suggesting that one invisible ghost is turning into another invisible ghost.
As the research highlights, gravitons are, and I quote, almost impossible to catch directly, since gravity's pull on individual particles is vanishingly weak, so searching for them feels like hitting an absolute dead end. But hang on a second, because theoretical physics actually suggests these gravitons might just possess a hidden vulnerability. All right, on to Section 3, the transformation effect.
This is the phase of our detective story where we actually find a mechanism to make the invisible, well, visible. And we do this through something called the Gertz-Stein effect. Now, I know that sounds like something straight out of a sci-fi movie, but I assure you, it relies on entirely established, non-exotic physics. The Gertz-Stein effect basically dictates that a graviton passing through a magnetic field has a tiny, small chance of actually transforming into a photon, a particle of light. So here's how this transformation actually goes down, step by step. Step 1, deep out in space, a dark matter particle eventually decays into a graviton. Step 2, that newly minted graviton bumps into a magnetic field. And step 3, thanks to the Gertz-Stein effect, the graviton transforms into a highly energetic gamma-ray photon. Just like that, an entirely invisible particle of dark matter has ultimately generated a flash of actual observable light.
Moving to Section 4, cosmic web crime scenes.
Now, the big question is, where exactly should scientists point their telescopes to actually witness this super rare transformation? Well, the answer lies in cosmic filaments. Picture this vast, gigantic web of thread-like structures spanning the entire observable universe, just linking clusters of galaxies together. These cosmic threads aren't just empty space either. They are permeated with weak but incredibly wide-reaching magnetic fields that stretch coherently across millions of light years.
And because they're just so enormously huge, filling up a massive chunk of the observable universe, these filaments act like the absolute perfect trap. If dark matter decays into gravitons anywhere along these sprawling magnetic threads, those vast magnetic fields can coax those gravitons into becoming a faint but steady glow of gamma-ray photons.
And this brilliantly illustrates a massive paradigm shift in astrophysics. For years, the old hunt involved pointing our instruments right at the incredibly crowded, noisy, chaotic center of our own Milky Way galaxy, just hoping to spot dark matter signals amidst all that mess. But the new hunt, proposed by Dunsky's team, flips that traditional strategy completely on its head. Instead of looking inward at the messy center, we look outward toward the distant, vast, and much, much quieter intergalactic filaments. Which brings us to Section 5, setting the first limits.
So how did Dunsky's team actually put this incredible hypothesis to the test with some real-world interrogation tactics? Well, they used the Fermi-Lat Space Telescope. The researchers meticulously combed through background gamma-ray data that Fermi-Lat had already gathered from across the entire sky. They were hunting for that specific, faint, steady gamma-ray glow coming from the cosmic filaments, the telltale signature of decaying dark matter.
And the result of this grand cosmic interrogation? Well, they found absolutely no unexplained excess of gamma rays. Nothing. Nada. Now you might be thinking, well, geez, that's a bit of a disappointment. But hold up, because in physics, a non-detection is absolutely not a failure. The really crucial point here is that by not finding an excess glow, the team was able to set the very first limits on just how quickly dark matter could possibly be decaying into gravitons. They established these strict mathematical boundaries across an enormous range of possible dark matter masses, telling future scientists exactly what thresholds we are working with. And hey, the hunt is far from over. In fact, there's a proposed successor to the Fermi telescope called the Advanced Particle Astrophysics Telescope, and it could soon sharpen these constraints by a massive factor of 10. That means our vision into the dark universe is about to get 10 times clearer. So if dark matter really does decay into gravitons, we finally got the blueprint. The filament scanning strategy proposed by the NYU team might just ultimately prove to be our greatest tool yet for catching that faint glow it leaves behind. We actually finally know exactly where and how to set our traps.
Which kind of leaves us with this absolutely incredible thought to ponder. If 85% of our universe's mass is slowly, quietly dissolving right into the very fabric of gravity itself, what other invisible transformations are happening right in front of us, just waiting for the right trap to be set? Thank you, fellow Focus learners, for joining me on this incredible cosmic hunt today. Keep looking up and keep questioning the unseen.